Okay, is that better? Good. Okay, so things are happening, as I said, quite rapidly now in the area of nuclear energy. I'm just going to hit highlights across some of the areas that I think are important in thinking about the question of what role nuclear energy is playing now and what role it could play in the future in terms of providing electricity and potentially hydrogen as well that would have very low carbon intensity. And so with that, I'm going to dive on in and show you some material. And I promise to make sure that I finish on time and leave a little bit of time at least for questions. So the first thing to do, of course, is to emphasize that right here, this institution and up on the hill, it's the center of the universe for nuclear science and technology. And if you go through and look at the history, the heavy elements, neptunium and plutonium, were discovered here by Glenn Seaborg. And of course, then running out of planets, and I guess Pluto probably was a mistake, we now know. Can you imagine, it might not have been plutonium if he'd only known that it wasn't really a planet. Then we have americium, of course, berkelium, referring to the campus, not to the city. Californium, referring to the state and the university. Lawrencium, of course, and then probably the only person who will have been alive and been able to point at the periodic table with his known name on it, Glenn Seaborg and Seaborgium. So first of all, let me just run through a list of things that have been happening recently that are relevant to the topic of nuclear energy. And so actually, one of the most important and relevant points is that we've seen enormous growth in the consumption of coal, being driven principally by China and India. And this coal is used dominantly to produce baseload electricity. Of the options that could be scaled to similar size that would produce baseload electricity, we only have one, which is nuclear. And so nuclear competes directly against this big global problem that we have. Now, when we look at what's happening in the United States, there's been essentially a transformation in our ability to run nuclear plants reliably. And this is evidenced when I joined UC Berkeley as an assistant professor in 1990. The average capacity factor of plants in this country was about 66%. That meant that 1/3 of the time our plants were down, either for extended refueling outages or for forced outages. Today, the average capacity factor is above 90%. And of that, less than 2% across the entire fleet is due to forced outages, which means that there has been a transformation in the capability to run these very complex, actually very old plant designs with a very high level of reliability. And this has turned them into the least expensive source of electricity that we have. Average production cost right now is below 0.7 cents per or 1.7 cents per kilowatt hour. And so this in turn has led to a lot of activity around license renewals and extensions. Essentially, by the end of this decade, over 70% of the plants are expected to either have license extensions in place or to have them being processed at the same time, simply because this has turned into one of the least expensive sources of electricity we have. Also, a very important point is that last summer, in summer of 2005, an energy bill was passed, which includes important incentives that make it much more attractive to consider the new construction of plants. These include loan guarantees, and they included production tax credits for new nuclear plants, the 1.8 cents per kilowatt hour that's also been given traditionally to renewable sources for up to 6 gigawatts of new plants. As of right now, we have a total of 19 plant sites that have announced that they're going to docket or submit construction license applications by the end of 2008 for a total at this point of 26 plants, which means that 5 of these sites are going to get construction licenses for dual unit AP1000s and 2 of them for ABWRs. Now, if you add up the total capacity, this is now over 30 gigawatts of new capacity, which would qualify for a share of this 6 gigawatts of production tax credits. And so at this point, it's pretty clear that the production tax credits are not affecting utilities' economic decisions to purchase these plants, because if there is indeed 30 gigawatts that come online within the time frame that's been required, which is to start construction by 2014, the production tax credits are going to be diluted to the point where they're actually pretty irrelevant in the overall decision. This means that the utilities that are making these decisions believe that these plants are a competitive source of electricity compared to building coal plants. And that's, I think, a very important point. Because, again, nuclear and coal compete head-to-head for baseload electricity generation. The other big area that's important from the perspective of national policy is the question of waste disposal. I'm going to spend some time updating you on where things stand also around Yucca Mountain, what the likely capacity of the site is, and what advanced fuel cycles could do to extend that capacity yet further. And then, again, pointing out that as of 2004, average production costs, this does not include paying off your loans for capital, but the fuel operations maintenance was 1.7 cents per kilowatt hour, average capacity factor above 90%. And indeed, nuclear electricity, nuclear energy, out of all of the energy that we use in the country, this is 70% of the non-fossil energy we have. And most of the rest is hydro. Okay. This is just going back 6 months from July. In January, we had 10 utilities, 11 sites, 16 new reactors, and so in the 6 months past that, it roughly doubled again. Let me give you just a quick tutorial on these sources of energy. First of all, nuclear fission. Well, this involves the interaction of neutrons with uranium, mainly fissile uranium or plutonium, giving rise to fission reactions, which release multiple neutrons, 2 to 3, and therefore have the capability to sustain a chain reaction. And the key point is that these reactions will release a substantial amount of energy, about 200 million electron volts. They also then will generate what we call activation products, which is where the excess neutrons get absorbed in other elements, and also, of course, the fission products. And it's these activation products and fission products that we worry about in terms of waste generation. If you want to go to macroscopic terms, 200 million electron volts translates into a rather large number of joules per kilogram of fuel. Or to put it into sort of quantities that are more easily understandable, a 1,000 megawatt fission power plant consumes about 3 kilograms of uranium per day, converting it into fission products, providing electricity. This would be sufficient for roughly 1/10 of Northern California, a plant of this size. And so the things that we generate in terms of waste include the fission products. Key ones to think about are strontium-90, cesium-137, technetium-99. We also generate a suite of activation products, including the fact that in some cases, when neutrons interact with uranium, they're absorbed rather than causing fission, building up heavy elements such as plutonium, americium, neptunium. And these actually are the dominant source of long-term hazard in spent fuel. These are also things which could be recycled and transmuted if we wanted to, and I'll come back to that after a while. Neutrons are also absorbed into structures. In general, these radioactive elements that are generated have modest half-lives and can be disposed of as low-level waste because within 100 to a couple hundred years, the radiation levels have died away to be unmeasurable. And then, likewise, coolants have very low to moderate activation, and transmutation could be used for these long-lived transuranics. It's not practical for the rather small quantities of long-lived fission products. And then, in thinking about any source of energy, we need to think about it from a life cycle perspective, particularly when we start talking about sources of energy that don't consume fossil fuels. And in that case, we want to look at construction and the mining of material. And so we need to be thinking about what happens when we mine uranium, and also construction materials, in most important being steel and concrete. Fusion may be where we get in the somewhat longer term. There are those of us who've worked on this problem. Fusion reaction also releases energies in the millions of electron volts. And what we're doing is we're reacting the two heavy elements of hydrogen, deuterium with tritium, generating helium and a neutron. That neutron can go on to cause activation. In fact, we want to make more tritium, and so we use these neutrons to make tritium. We can have a self-sustaining fusion power plant cycle. This is another big number in terms of density, but to put it again into perspective, a 1,000 megawatt fusion power plant would consume about 1 pound of fuel per day. In terms of the waste that you would generate, it would be much, much smaller than what we get with fission, mainly because you don't need to have heavy elements around like uranium that can form these long-lived transuranics. And in fact, if we're careful in selecting materials, we can end up with very moderate amounts or small amounts of radioactive material, most of which decays rapidly. We still have to think about steel, concrete, and other material inputs. Now we can contrast this to energy from fossil fuels. For example, when we take coal and react it with clean air, producing carbon dioxide, water vapor, and actually a bunch of other things as well that are not so clean. And the energy density in fossil fuels is 20 to 30 megajoules per kilogram, which means that the same power plant powered by coal burns over 7 million kilograms of fuel per day. And in fact, this is a massive quantity. 70% of all of our rail transport right now in the United States is hauling coal from Wyoming to other places to be burned. And so if we look at the waste products, of course, all of this 7 million kilograms per day is going to be discharged out into the environment, and we'll have nitric oxides, sulfur oxides, ash, and of course carbon dioxide. We also have substantial environmental impacts due to the very large volumes that are mined, leachates and dust from the mining, and again, it takes material to construct these plants. Let's see, there. Okay, so let's take a look at one possible example for what nuclear energy can do, which is France. And France had a policy to replace the use of fossil fuel in electricity generation with nuclear. And in fact, they accomplished that goal in a 20-year period. They are now less than 10% fossil energy total in their electricity generation, and they're dominantly, therefore, electricity supply from nuclear energy. And this pretty much had a big impact. France was invaded by Germany in World War II in part to get the coal mines that France had. And they closed their very last coal mine in April of 2004 because it's no longer economic for them to produce coal given the very, very tiny amounts that are now used industrially there. Germany is a different country, and they rely extensively on coal strip mining. This is not photoshopped. This is how they mine the stuff. And you know, so this thing actually takes as long to construct as a nuclear power plant. And it consumes similar amounts of steel and stuff. This is one of their big machines that they use for just ripping up and strip mining coal in Germany. In fact, this points to the fact that the use of coal is a massive, massive enterprise. It is mind-boggling when you look at what is actually going on around the mining, transport, and burning of coal. California, we use electricity from a variety of different sources. This is the breakdown in 2004. Over here you can see that nuclear is about 13% of the total. We have a substantial amount from natural gas, which is expensive these days. Large hydro, which was developed mainly before World War II, and some geothermal. And then we actually import a lot of coal electricity. Currently about 20% of our electricity generation comes from coal, electricity imported from the Southwest. And so we might want to think about what we could do to replace this chunk at least in the future. It could be worthwhile for us to do this, particularly because if we're successful in getting carbon caps or carbon taxes in place, which could very likely be happening, this will become much more expensive. Right now, this is very inexpensive electricity, and it would become more expensive if we had carbon caps. So to think about sort of how to compare different energy sources, one of the best measures that I've found is to actually look at the construction inputs to build the infrastructure. because you can make claims about costs and dollars and stuff, and there's lots of ways that you can tweak those numbers. But the amount of steel and concrete it takes to build a plant is hard to conceal or to try to hide. And so for nuclear, the numbers for the types of plants we were building back in the 1970s and that are operating today are around 40 metric tons of steel per megawatt of average power output and 190 cubic meters of concrete. We can compare this to wind, and the same average power output generated from wind requires an investment of 460 metric tons of steel and about 870 cubic meters of concrete for a site with a relatively good wind capacity. Interestingly enough, coal is a technology that also takes a lot of material, boilers, steam turbines, all of this. And in fact, it takes more steel to build coal plants by over a factor of 2 than is necessary to build nuclear plants, which suggests that this is not the right thing for us to be building a lot of new plants, even though we are currently in the U.S. And then this illustrates, sort of the energy policy when we had inexpensive natural gas and thought it would stay inexpensive for multiple decades. When you start using gas turbines, things that you can hang on the wing of an airplane, which you don't do with a coal power plant, but gas turbines, what we see is that the amount of material required to build this type of plant is very small, and this is why, in fact, the capital costs are also very small. Okay, well, we make projections about what's going to happen over the next several decades in terms of energy consumption, and the Department of Energy has an Energy Information Agency that makes these projections, and this is the most recent from 2006, their Energy Outlook report, where they are projecting at this point 6 gigawatts of new nuclear plants. Now, of course, if you were to go back about 7 or 8 years ago, they were projecting that we would have premature closure of most of our existing nuclear plants. And in fact, if you were to sort of plot the projections of the Energy Information Agency about future nuclear power plant roles, say out in the 2025-2030 time frame, versus the year that they made the projection and plotted it linearly, we'll have 100% nuclear energy for everything out by 2030 if we stay on this trend. But that aside, what they tell us is that it's going to make a lot of difference what the capital costs are in these plants in terms of how much new capacity one would predict is going to be put in. And this is all, of course, without any carbon emissions caps or trading. It would be different. And anybody who thinks by 2015 we don't have a carbon trading program in the United States, raise your hand. And so at any rate, because then, of course, you'd have less of a tendency to see this big spike upward in coal and in natural gas, and maybe some of the non-fossil stuff would start to kick in. But at any rate, another important point is the question of how well we can drive down these capital costs over the coming decades, because this also has a big effect on projections for how much new capacity might be built. And here's what the most recent numbers are in terms of actual construction costs that are being predicted by the vendors for these plants. And so we're sitting somewhere here in the mid-range. I think this makes it a very interesting question what we can do as engineers to improve the technology so that you can get these larger reductions in the capital cost for construction out over the next few decades. I think this is something where there's some potential. Now, another thing that's interesting to look at is what's been happening around these material inputs. The plants that we were designing and building back in the 70s were actually very efficient in their use of things like steel and concrete. We had the 3 Mile Island accident, which revealed substantial flaws, actually major flaws, both in how the industry was run and also in our understanding of and design of nuclear plants. In response, the plant designs that came out in the late 80s into early 90s, such as the EPR and the ABWR, involved basically massive additions, more structures, more safety systems, and a whole bunch of additional active equipment. And these plants have turned out to be expensive to build. these are the ones that push up towards the $2,000 per kilowatt range for new construction, although the ABWRs that we have built have been built in 48 months and have started up flawlessly, all of the ones that we've built in Japan. The big change has been to develop passive safety systems for these plants which eliminate a large amount of the active equipment, pumps, diesel generators, big heat exchangers, external heat sink, and the space needed to house them. And this has resulted in substantial reductions in these new passive plant designs in the quantities of material required to build them, and therefore also in the capital costs. And in fact, at Berkeley, we did a major fraction of the work in developing the passive heat exchangers that are used for the decay heat removal in the ESBWR. And if you're interested, you can grab a copy of the forefront that's out there, because there's an article in there that describes some of the work that was done that made those changes. Let's see. There we go. And this is just another, we can look at building volume, concrete volume, amounts of steel, and these are water-cooled reactors. We start getting interested in various types of high-temperature reactors. So this is the pebble bed reactor that's being developed in South Africa. This is the GTMHR, which is from General Atomics down in San Diego. This is the Berkeley, the one that we work on, because we've got some ideas also. Now I'm going to go through and spend some time talking sort of about what are the environmental, public health, worker safety issues, and then I'm going to spend a little bit of time on reactors and close with nuclear waste. First thing to do is just to point out that we have some potential sources of electricity that can have very low emissions for carbon dioxide compared to fossil fuels. I think it's really important for us not to argue about whether wind or nuclear has more or less, right? Because as engineers, we should immediately recognize that both of these numbers are zero compared to these. And so the important thing to do is to displace this stuff with some of this stuff. It's not to say that we need more or one or the other of these simply because there's maybe some disagreement as to what belongs in those numbers, and so on. If we take a look at what goes on, we should also be focused again on the question of what happens to workers and to public health. In particular, because we have regions in the world, especially China, but also India, Ukraine, where worker safety conditions are abysmal within the industries that produce coal and fossil fuels in general. Estimates are that 5,000 workers per year, for example, die in Chinese coal mines right now. And that's compared to, in the United States, we're down at about 100 workers per year fatalities in our coal mines. And so it's still a big number compared to, the nuclear industry, for example, if we kill a worker in the nuclear industry, we're on the front page headlines. And the last time you saw that was several years ago with 2 workers, actually ended up being 3, that died in a radiation accident in Japan. And so it doesn't happen in our industry. And so if we go to things here are the statistics for the United States in terms of the average numbers. And basically, if you add this up, our coal mines have about 100 fatalities per year on average. And this is much better than what we had back in the 50s because we've made big improvements. We can look at, in nuclear industry, the worker safety is more around lost time accidents. And so these are the nuclear numbers, and I've multiplied them by a factor of 10 because otherwise they would be way down here and you wouldn't be able to see what they look like. And so what we see is that working, lost time injury rate in nuclear power plants is about 1/4 what we have in offices. And it's about 1/10 what we observe in traditional industries, mining and elsewhere. And this also points to basically the practices that we have around safety and reliability that make sure that the workers have thought through everything they do beforehand, and they work very aggressively to keep the work environment extremely safe. We see other evidence for healthy worker effect. There was a major study of 54,000 nuclear power plant employees looking at the potential for health effects from exposure to radiation. In general, what we find is that if you are a nuclear worker in a nuclear power plant, your mortality rates compared to the general population will be 1/3 less for all cancers, 66% for all non-cancer sources of death, giving a total of 60% lower rate of mortality, which basically means that if you go work in a nuclear plant, presumably by these statistics, you have a 2.5 times lower chance of dying than if you're not working in a nuclear plant. Now, this actually seems pretty good, but you need to think about this from the perspective of actually this might be, it's not because of the radiation exposure, it's probably because you work in an environment where safety is emphasized. You probably carry those practices over in terms of buckling your seat belts and other things when you get out on the road and do hazardous things, actually much more hazardous than you do in your work environment elsewhere. And it might be because you're well paid and well educated and you probably don't smoke, right? And that's probably what you're seeing here. But from that, you can try to tease out, well, if you look at the radiation exposures, is there any health effect that's detectable? And the answer is that if there is, it's very small. In fact, in this study, they could not determine any effect statistically detectable from low-level exposure that workers get. Okay. Now, if we want to compare sort of the public health impacts, we can do that by looking at what we understand happens because of our use of fossil fuels. And what we know is that fossil fuels are suspected to cause as many as 64,000 premature deaths each year, and this is just due to the particulate exposure. You know, right now the best estimates for the total number of premature fatalities or deaths that will come from the Chernobyl accident, which is the worst accident in the history of nuclear energy, range from 4,000 at the sort of the UN estimate level to the 20,000 level that you get from some of the other activist groups. And so you could say that, in essence, our use of fossil fuels in the United States alone is equivalent to 3 to 10 or so Chernobyl accidents happening in terms of the public health impact. So then, if we look at what's happening around the technology, of course there's been evolution from the very early prototype reactors. Fermi 1 had a meltdown accident. These reactors basically were very much on the early part of the learning curve. To the plants that we have built and are currently operating, we call these Generation 2. 3 Mile Island fit in this category. To the new designs that have been developed, which are the ones that are actually slated for the new construction in the United States. And then finally, to additional ones that have the capability to do things such as produce hydrogen, work with dry cooling, recycle and transmute waste. And these are being developed by the DOE and internationally as we speak. This is a picture of the economic simplified boiling water reactor. 3 of these units are being prepared for construction licenses. General Electric is ordering the major reactor components as we speak, or has ordered them, because they have long lead times. And so this is a passively safe plant, and it's one that actually we did a lot of work on. All of the big active safety equipment has been replaced by a small number of little heat exchangers here. And at Berkeley, we did the work to develop the ability to model and to predict the behavior of those. This is the AP1000, which is the Westinghouse plant, also passively safe. And then to begin to point out, a little bit about where things stand in terms of the current ability to build these things compared to what it was like 25 years ago. We know that in every other field, there has been major changes in technologies for manufacturing and construction. If you go to the shipbuilding industry now, ships are constructed in factories using automated manufacturing methods and are literally assembled like Lego blocks to build the ship out. And you weld things together, and you can put together these big cruise ships, for example, now are built in 1 year. And if you've ever seen one of these things or been on them, it's amazing to think that you could do that. So the interesting question is what's going to be different when you apply these modern tools for design and construction to the design and construction of new nuclear plants. And so one of the things that's happening is that we're moving much more towards the modular construction, where large units of stuff are built separately and then assembled again by Legos, and concrete is poured. And so this has been able, at this point, actually, to actually being online commercially in Japan. They've done that. The record now is down at around 46 months. And the new designs have been optimized for even more rapid construction. We'll see what we achieve, but things are changing there. Another major thing that's different is it emphasizes the importance of the computer-aided design capabilities, is to look at how we designed plants back in the 1970s when they were all done with paper and pencil, with drafting on two-dimensional drawings. All of the control of components and stuff, keeping track of equipment lists, was done manually. And in order to make sure that you could build the thing in 3D, they would actually build plastic models. And of course, these days, we can do four-dimensional design. That is, we can even model the emplacement of major equipment components and the whole construction process, in addition to having complete 3D models for the plant as well. Okay. This is looking at some of the things that are coming up in the little bit longer term. High-temperature gas-cooled reactors are interesting because they can produce electricity with much higher efficiency, since they drive Brayton cycles rather than steam Rankine cycles. They also can be dry-cooled, so they can be sited in desert or arid regions without needing cooling water. And they have outlet temperatures that are hot enough that you can hook them up potentially even to make hydrogen directly through thermo-chemical processes. And indeed, this is the one that's being investigated most intensely right now, which is called the sulfur iodine process. Process heat comes in, water comes in, and out of the plant you get oxygen and hydrogen through a series of chemical processes. Now, to move to the final topic I promised to cover, which is waste management. In the United States, we have had a long and protracted and difficult process in order to identify and select a site for a new or for a repository for high-level waste and spent fuel. And that site is at Yucca Mountain. This is about 90 miles to the north of Las Vegas. Right over this third here is Bureau of Land Management owned land. This part up here, Yucca actually sits on 3 different plots of land, because this is Nellis Air Force Base, and then this part right here is the Nevada test site. If you go about 10 miles off in this direction is where you'll find all the craters and stuff from all of the waste that we've already put there under perhaps much less controlled conditions. And so Yucca Mountain has been actually selected by the United States as a site for a repository. And it's an important question how it will perform technically in terms of providing long-term isolation for spent fuel. And so, first of all, just to introduce the configuration, Yucca Mountain is unique among the types of sites that are being considered for repositories because it's not located below the water table. This creates advantages and disadvantages. Overall, it probably increases the flexibility of the site in ways which make it a more attractive site than a saturated one. The key point is that you can pump air from outside through these drifts for multiple decades to continue to remove decay heat from the waste after it's been emplaced. And this gets us to the whole philosophy behind geologic disposal, which is we know, for example, 100,000 years from now, right here in Berkeley, things are going to be much different, right? If you go down 1,000 feet, things change much more slowly. And in fact, when we look at deep geologic isolation, the main reason that it's interesting is because of the fact that you can extrapolate from what's been happening over the last many million years into what might happen in the future. And in fact, the biggest scientific challenge that is posed in developing a repository is predicting what the effects are from having perturbed that environment, both by drilling the tunnels in it, but even more significantly from the release of the heat from radioactive decay, which heats the ground, changing the hydrology, changing the chemistry, and potentially even causing permanent changes to the composition of the rock. And so controlling and modeling heat is the major thing that's done. A lot of work at Lawrence Berkeley Lab, Lawrence Livermore Lab, and also at Sandia in this area has developed a pretty good understanding. If we look at advanced fuel cycles, we have the potential to go even further in terms of developing ways to control the heat and increase the capacity of a site like this. Now, the thing that we're trying to do is to assure that over the next 1 million years, groundwater that might leach through the repository, contact the waste, and then transport radioactive material down to the water table and then about 10 to 12 miles to the Armagosa Valley, where it becomes shallow enough that people could use it for irrigation, that people using that water would not be exposed to doses that would exceed what they would receive from natural radiation sources. This is the current thing that the DOE is required to prove, that for the next million years, that would be the worst possible thing that could happen. And so this would be a picture of what that plume is predicted to look like. You can see that out here in the Armagosa Valley, you might contaminate a fifth to a quarter of the groundwater if indeed there's some sort of release here. And it's required that the very center of that plume, if you were to put in a well, that this is the worst possible outcome. Of course, if we think about it, we need to sort of contrast that to what we've already done to groundwater. And so this is California. And this is all of the wells that we've already contaminated with nitrate. These are all the wells that we have contaminated with perchlorate. And then, of course, nature does this too. And so these are all the wells where it's dangerous to drink the water because of arsenic. And so sort of the worst case outcome from having done Yucca Mountain is that you'd have a couple more, or 1 or 2 more yellow dots down here in this little box, which is where Yucca Mountain will be. And the interesting thing is that it's technically quite plausible that we can provide reasonable assurance that all of the things that would have to go wrong, the combination of all of them going wrong, is sufficiently unlikely that indeed for the next million years the groundwater will not get contaminated in these areas. Now, if we wanted to increase the capacity of the site, and we would need to do that if we're going to build new reactors, the first thing we need to do is to remove a statutory limit on the capacity. In that case, then the technical limit for spent fuel, well, for the 2,000-acre site would be, this is the amount that we would produce by 2014. This is the total amount that our reactors that are currently operating would produce. We could build another 100 reactors and still be well in, and then given the amount of extra area, we could probably build a couple hundred more before we would be stressing the capacity of the site. But when we look at what advanced fuel cycles can do, if you recycle the heat-generating actinides, which dominate the load, in fact, we get factors of 50 increase. And so my best estimate is that the site, if it was only used for the fission products, and we put in about 800 kilometers of drifts in this 4,000 acres, would be equivalent to the energy production that we get from 1 trillion tons of coal, which is about 1,000 years of U.S. current coal consumption. In other words, it's relatively large if we go to, but there's probably not a need to rush in any case because the site, even for spent fuel, has a lot of capacity. This is a list of what's been happening. Yucca Mountain is a politically divisive project. It's being run by the Department of Energy, which is not renowned for its ability to do big projects in the nuclear field with a lot of finesse. So it's about a factor of 2 behind schedule, and it's over budget. But we did the whole same thing with the WIP repository in New Mexico, which is taking military transuranic waste. Eventually, it's possible that we can get there. And this requires a couple of big steps. We want to get the final EPA ruling that will shift from a 10,000 to a million-year safety standard. We want to then get a license application docketed in 2008 with NRC review. A few things that could be done in terms of policy, like removing the cap and putting in place some other measures, would basically then allow this to be used as a flexible site that would be capable of handling all waste that we might generate conceivably in the next 100 to 200 years from using nuclear energy. Okay, so some conclusions, some things. Well, we do have a waste repository site in the United States. Let's see how much further we can go. We'll actually know a lot within the next couple of years when the license application goes on. And then you can see the rest of it. This is all stuff that I've covered. It's probably good for me to just go ahead and stop here so I have at least a couple minutes for questions.
Many of you don't know this is being web connected to UC Santa Cruz, UC Davis, and UC Merced, which is what we traditionally do, but often we don't notice that. To show the importance of this talk, we had 4 questions sent to us during the casting, which is great. So if you don't mind me asking a couple of questions from these sheets first. So from UC Santa Cruz, can you comment on the environmental impact of nuclear fuel extraction? It's about the nuclear fuel extraction part.
Right, and so this is talking about reprocessing of nuclear fuel. And the environmental impact from doing that can vary. The main point is that when you reprocess fuel, there are some of the elements which are easy to keep in the reprocessing plant and others which have a tendency to be hard to keep inside. In particular, you have a tendency to release krypton, which is a noble gas, has very, very small public health impacts. The French, when they reprocess, discharge krypton plus some iodine and plus some tritium. And so what you want to do is you want to compare the public health impacts from doing that to what we routinely accept from other things that we do. In particular, if you compare it with what we do with fossil fuels, there's no comparison.
The next question is about the mortality rates of miners that harvest the nuclear fuel compared to that of the general population.
Yeah, that's correct. I do not have specific statistics for what happens in hard rock mining. However, it tends to be significantly safer, particularly because a fair amount of the hard rock mining or the uranium mining now occurs in open pit mining, which is intrinsically safer. But the volumes of material that are involved are vastly smaller, and coal is intrinsically, especially underground, more difficult and dangerous thing to mine simply because it's so soft and you have this tendency to have these collapses and cave-ins.
Paul, excuse me for interrupting. Maybe we should take a question from this audience and then go back to the Santa Cruz questions.
Yeah.
Would that
So
be fair?
an audience from the floor? Oh, sorry.
An audience
question from the floor.
Let's go back here to the
An audience from the floor. That could happen too, I guess.
We have an audience on the floor.
Thank you. Wonderful talk. I'm wondering, in the current oil industry, a lot of time is spent looking for new reserves, and I'm wondering if you could comment on the estimates for uranium in the earth and how easy it would be to continue supplying these 3.2 kilograms.
This is one of the topics that's cropped up, and so there's a couple of important points. The first is that we've not had a lot of exploration activity in the last 15 to 20 years, mainly because we had the collapse of the Soviet Union. And so currently, over 50% of the electricity that's generated in nuclear plants right now in the United States is coming from burning highly enriched uranium that has been downblended from Russian nuclear weapons. And so, of the 20% we get from of our electricity from nuclear, over half of that is coming from downblended stuff. This has, of course, caused the uranium mining industry to be very, 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 essentially dead. There's been a huge expansion now. The key thing that's interesting is that even though the prices of uranium have gone up by over a factor of 2, you don't even notice that in the cost of the electricity because the cost of the fuel is actually such a small fraction. So we're not particularly concerned about the market having bad impact if uranium prices go up and down enough to get new mining activity to start up. In the longer term, we currently use only about 1% of the energy content in uranium given the current types of reactors that we have. As we transition towards fast reactor technologies, we can extract much larger fraction. As soon as you've done that, then there's enough uranium sitting in depleted uranium at places in Ohio and Kentucky that you're not going to, Tennessee and Kentucky, you're not going to run out for centuries if you're using that stuff. Yeah.
One more here, Paul.
Another question from here?
Yeah, like you said, like reprocessing is such a huge deal. It could save us from having to mine uranium for centuries, and it will save us so much space in Yucca Mountain. But we don't do it here. And what as a do you know more about how long it might take?
I have two different talks. One of them I give when I think I'm going to be faced mainly by skeptics, which challenges their side of it. And one of them I give when I'm faced with people I think are enthusiasts, when I need to challenge some of their assumptions as well. Building and deploying successfully nuclear infrastructure requires a lot of effort and careful work and preparation. So I think that for us, I am confident in the longer term that we will develop and deploy reprocessing technology. The main point is that if we rush into it, we're likely to get it wrong. And we have had enough examples of not doing these things correctly. I think we need to get some of the experience from building these new light water reactors because we'll learn a lot. But in the longer term, we can make the transition, I'm confident. There's no technological obstacle because we know the French are very successful. The Brits have had real bad problems. So.
Another question from Santa Cruz that asks you to compare to wind, solar, and geothermal. They say anything look good compared with coal. So how does nuclear compare to wind, solar, and geothermal?
Right.
Surely the risks are lower with those technologies.
Yes. I mean, the things that we have to look at are the costs, but also the geothermal, of course, also is a baseload type of electricity source. And so to the extent that we can develop it, it competes directly with coal as well. The problem, of course, with geothermal is that the way that we currently do it's not renewable. We deplete wells and we close them in just like we do with natural gas. So, in fact, it's not really a long-term solution unless you go to much more expensive dry rock. In the case of wind and solar, they're intermittent, and so the majority of the time they're actually not providing electricity, and we're backing it up because it's the only economic way to do it with natural gas. So what wind and solar currently do is they reduce the amount of natural gas that we consume, but they do not, in the way we currently structure our market, compete against coal. And it's questionable that if you put in the storage that would be needed to make them look like a baseload source, that you could afford to pay for it.
Sorry, Gary, you go ahead. Sorry, you were watching the group. Sorry.
Hi. One question. What is the current state of nuclear fusion technology? My current understanding is that it's not a question of if, but when. And is this constrained? Is the time to market constrained by the amount of research funding that it's getting, or what is the current state? Thanks.
That's a wonderful question. I cut out my fusion slides mainly because I still pushed very much against the time limits. But basically, the current status for fusion is that we're in the process of constructing facilities that will provide the scientific demonstration of viability. That is, that you can get more energy out than you invest in. And one of those facilities is the inertial confinement approach, National Ignition Facility. The second is ITER, which is being built in France. We should expect that within the next 5 to 15 years or so, we can have demonstration of scientific viability. Another 15 to 20 years then is required to come up with an engineering system that can actually pull out useful energy from doing that. And then we have to see that it's commercially successful. And it's adding up all of those time periods that generally gives you the 40 to 50 years. But we're going to know a lot within the next 10 years or 15 years simply because we will have the scientific demonstration that it's actually feasible to make energy with fusion.
I know Gary Baldwin has a question, so I'm going to hand over to
looking out at this audience and the attendance today, you'd think that energy was a topic on the minds of people. Obviously it is. But also national security, world security, international security, and given the events of the last few days, the relationship between energy creation using nuclear means and the possibility that the byproducts or the pre-products might get into the wrong hands springs to mind.
Of course.
So could you comment on, how would I phrase it, the fear factor or anything that you'd like to say in terms of the relationship and the security threats?
Let me try to provide a brief answer to that question. We face two primary categories of threats. One is from proliferant states that are trying to acquire technology, and there we have two bad actors, Iran and North Korea. In that case, we're not going to change either the behavior of Iran or North Korea by what we do on the civil side. But we are right now on the crux of a big an important decision, which is whether or not we're going to put in place internationalized fuel cycle centers that eliminate and make it economically and from a security perspective unattractive for additional states to acquire enrichment technology in particular, but also reprocessing. And one of the reasons why we need progress on Yucca is that if the United States doesn't take back foreign spent fuel in modest quantities, much less than we actually make ourselves, to sweeten this deal, we could indeed see Venezuela, Indonesia. These are countries that are seriously looking at developing new nuclear plants and that are not particularly attracted to us, and that Iran has been talking to. The other areas in the security of nuclear materials, and that continues to be dominated by very poor physical security of some materials in the former Soviet Union, and we need to provide a consistently high level so that you can't steal the stuff either.
Did that get your question? One more minute, one more closing question from the floor. Eli Leyland, you get the opportunity to ask the question. And then I'm sure Professor Peterson will stick around for a little bit for people who want to come up informally. But Eli, please go ahead.
Can you comment on some of the other sources of controversy surrounding Yucca Mountain? Is it just potential for groundwater contamination, or I've heard things like it's
I know.
on a fault line, or people are worried about transporting the stuff, et cetera. Like, what else is there to that?
Sure. The first thing is that I should mention that I grew up there, and I grew up in Nevada, so I'm a Nevadan and stuff. And frankly, Nevadans are not happy that they were picked for this purpose. Okay. Now, I can step back myself and say that it's in the national interest to this is the test site. This is not pristine virgin area, and the big question is the safety standard that's been adopted, the million-year safety standard, sufficiently rigorous, and compared to anything else EPA requires, it is vastly more stringent. And the second question is it technically possible for the site to meet that standard? And the answer is we'll find out in 2 years, but I expect it probably will. The final question is, what about the ancillary activities, particularly transport of spent fuel? And there is concern about the safety of transport of spent fuel. However, whenever people voice serious objections and talk about it, they never, ever look at what we do with chemicals in terms of transporting hazardous chemicals. So if you're talking about what would be attractive targets for terrorists, just take a look at the fact that we have to ship liquid chlorine into all of our urban centers because that's how we provide safe drinking water. And so when you step back and look at the bigger picture, you can easily convince yourself that transporting spent fuel is not going to significantly increase the risks that we already take with transporting materials, and that there's better places for us to devote our attention.
Well, look, I think you'll agree with me. Every single question was so well-rounded and answered in a really deep way. This is obviously a fantastic expert in this field, and I can't thank him enough for really being here today. Thank you so much, and let's join.
Thanks, Bob.